All right, good morning. Happy Friday. Hey, listen, I'm not sure what's going on. I don't know if the district's messing with the network but we had some glitches at the end of the last period. So I might lose you completely. So if I do lose you, make sure you watch the video on YouTube of the lesson. So it's a new lesson in 12.1. It's only part one of it because I want to spend the rest of the time working on this practice AB. So this new lesson is focusing on arithmetic sequence, which should have been taught in Algebra 1, but I'm not assuming that it was taught. So trouble, reuniting if we have technical problems, make sure you watch the YouTube video, okay? Okay. It doesn't automatically download. It takes WebEx a while. So it'll be available for sure tonight or all right. I'm looking at your work from the past test, and one about this is check your work thoroughly. And I was looking at your scratch paper, and there wasn't one student whose work looks Can you guys hear me? No?
You're cutting out a lot.
Okay.
Yeah, you're cutting out a lot.
We'll keep trying. See, as long as you're moving, I think you can hear me. Can you hear me now? Yeah. So I was looking at your work on the last exam, and it didn't look good. Like, for example, I didn't see you restrict the domain when you were finding the inverse. Your notation is not good. When you take the square root of both sides, you're not putting plus or minus. So the notation in your work just does not look up to par. Now, the reason why that scares me is because next year in honors pre-cal, whether it be me or Mr. Johnston, we're not going to accept work like that. So you guys need to, I'm modeling the work for you. Make sure that you're doing the work that way. We are less concerned about correct answers. We're more concerned about you being able to work through a process and showing correct mathematical notation. So just know that I'm not happy with your work. Even my A students, I'm not happy with it. So you've got to show better work, okay? Otherwise, next year, it's going to be rough for a while next year. So just try to do what I'm doing in class. All right, so the first thing I want to do today, if we don't have a bunch of technical problems, questions you might have about solving radical and rational. You guys there? Anybody want me to work a problem? Now remember that we am on Tuesday morning, right? So Tuesday morning at 8 o'clock, you have an exam on 11, 1, 2, and 3, right? Okay. Keep nodding your head and stuff because I'm not sure if you're losing me or what's happening. All right. Anybody want me to work a problem from 11, 3? No? No problems? Okay. Well, I'm going to teach part of 12.1. If things are going bad, make sure you speak up or send me a remind message or something. I have my phone in front of me, so make sure you send me a remind message if things start going wacky. Okay? All right. So I'm not supposed to teach this, because supposedly you learned it in Algebra 1, but I'm not assuming that. Because you have to know about arithmetic sequence, you have to know about arithmetic series, you have to know about geometric sequence, geometric series, and infinite geometric series. So there's a lot of things that we're going to be doing here. So this is arithmetic sequence. Can you guys just say this to yourself? It's not arithmetic, it's arithmetic. You just say it to yourself, say it out loud. Okay, this is California Common Core Standard F-BF.2. And what I'm going to do is I'm going to give you some vocabulary, and it's probably not going to make any sense, but I'll make it make sense. So here we go. So the first term is a sequence. And a sequence is an ordered list of numbers. Okay, now I'm going to pin myself, so make sure if things start going haywire, make sure you let me know. Okay, today we're going to look at an explicit rule. And an explicit rule defines the term in position in, and I'll be talking about that, in position in as a function of n. Then we're going to look at a recursive rule by relating it to one or more previous terms. So I'm using a lot of words here that you may not know, like what does position mean? What do terms mean? What am I saying? So I just want to show you what we're going to be doing. So basically, you're going to have a horizontal table, and you're going to have an X and a Y that are now defined as n and f of n. So X and Y. Okay, the n, think of it like a position or a slot. And sometimes the positions start at 0 and sometimes the positions start at 1. So what this reminds me of is the horse races, because the horses go in position 1, position 2, position 3, position 4. They can't be fractions because you can't have 1.5 position. So these are integers that are the y value, or f of n, is the term. So this n is a position number, and this y, or f, is the term. And that's what all this is saying over here. So it says the explicit rule defines the term in the position in as a function of n. And so now I want to show you, this is arithmetic. And I'm going to show you why, and then I'll give you the definition of an arithmetic sequence. So if I take 8 minus 6, 10 minus 8, 12 minus 10, 14 minus 12, I get 2, 2, 2, and 2. Now, first of all, did you see how I did that? I didn't say 6 minus 8, 8 minus 10. I went backwards. So I took the successor minus the one prior. So I took 8 minus 6, 10 minus 8, 12 minus 10. That's how you find it. This number, because it's the same, is called common. So this has a common difference. D equals 2. What makes it arithmetic? Arithmetic sequence. You guys? Okay, are you guys there?
Yeah, it's just really laggy for me.
Yeah, we can barely see the screen. Yeah.
It was frozen.
Can you guys hear me? Are you there?
We can hear you now.
Yeah, I can hear you.
Okay. Okay, an arithmetic sequence is a sequence where consecutive terms, consecutive means one right after the other, have a common difference.
I like how Mike's is 100%.
Yvette, can you mute yourself? Yvette, can you mute yourself? All right, so you might see something like this, and they want to know, is it arithmetic? So you're going to take 3 minus 1, 5 minus 3, 7 minus 5, and 9 minus 7. And this is arithmetic because it has a common difference. Common means the same. If it doesn't have a common difference, it's just a sequence. So it's just a plain sequence. Pretty easy, right? So you would have 4 minus 2, 16 minus 4, 25 minus 16, 36 minus 25. Is that right, you guys?
Yeah.
So that's definitely, it does not have a common difference. So this is not arithmetic. Okay, so what we're going to look at now Okay, guys there? All right. Now, this is when the table starts with 0. And it must be arithmetic. The explicit rule looks like this. It looks like f of n is equal to a plus d times n, where n is greater than or equal to 0. I'll explain that in a minute. Here's the recursive. The recursive rule looks like f of n is equal to f of n minus 1 plus d, where n is greater than or equal to 1. Can you guys look up here for a second? All right, now this is when the table starts at 0. You're going to have 2 more rules when it starts at 1. This A is the initial term or the first term of the sequence. And that D is the common difference. Okay, so if this goes on like this, happens.
No, you got it.
Okay, can you hear me now?
Yeah.
Okay, if this continues to happen, I'm just going to stop the class and you'll have to watch the video. Okay? We'll see. Thanks for all your messages. You guys are blowing up. Did you hear what I said here? Is it me?
I can hear you.
Here.
We can hear you now.
Yeah.
Did you hear what I said about n being the position number, a being the first term, and d being the common difference? Okay.
I heard that.
Okay, now I want to say something really important before it cuts out again. This is f of n. So this is not distributed f. This is a function right here. But wherever you see an n, you're going to put the position. Wherever you see an a, you're going to put the first term. And wherever you see d, you're going to put the common difference. And I'm going to be doing an example in a minute, but I want to give you the rules first. You guys still there? Okay.
Yeah.
This should say initial term is 1. Should say is 1, is 0. And this should say the initial term is 1 with a common difference Okay, so these are the same type of rules, but this is when the starting position is 1. Okay, so here it is. The first one is f of n equals a plus d times n minus 1, where the domain is n greater than or equal to 1. And the recursive rule is f of n is equal to f of n minus 1 plus d, where n is greater than or equal to 2. Okay, look here real quick, please. This is distributed. So this is d times Let's take a look at an example. So we're going to use the table to write an explicit and a recursive rule. Here's the table. So n is the position, and f of n is the term, and that is x and y. So the position is starting at 0, which means we're using the first set of formulas for the rule. And here are the terms: 2, 5, 8, 11, 14, and 17. Now, here's the deal. We do not know if this is arithmetic. They didn't say anything. And so we can't assume that. So the first thing you're going to see me do is to see if it's arithmetic so I can use the rules. So here we go. We have 5 minus 2, 8 minus 5, and you must do them in this order. 11 minus 8, 14 minus 11, 17 minus 14, and we're checking to see if we have a common difference, which we do, which means it's arithmetic. So see, your starting position is 0, right? So we're going to use the first set of formulas. So the explicit rule is going to be f of n is equal to a plus d times n, where n is greater than or equal to 0. Now remember that a is the initial term and n is the domain, and n is plus the common difference times n, so that's the rule. And watch how I write the domain. The domain is greater than or equal to 0 and less than or equal to 5. That represents our table. So that's the domain, which are the positions that represent the table 0 to 5. The recursive rule is f of n is equal to f of n minus that. So our recursive rule is going to be this. There's nothing to do with that, and that's a function, so don't distribute. Plus 3, where n is greater than or equal to 1 and less than or equal to 5. And if you're wondering, hey, where did the 0 go? Where did the 0 go in the domain? You're going to find out. You're going to find out. Let's do another problem where we start at 1 this time. You guys okay right now? Okay. So see how we're starting at 1 this time? And our terms are 29, 25. You still find the common difference the same way. 25 minus 29, 21 minus 25, 17 minus 21, 13 minus 17, and 9 minus 13. So we get -4, -4, -4, -4, -4. This is arithmetic. So the common difference is -4, and we can use the rules for a starting position of 1. So now the second set of rules, this is f of n is equal to a plus d times n minus 1, where n is greater than or equal to 1. And that makes sense, right? The domain, it started at 1 this time. So we have the initial term, which is 29, minus 4 times n minus 1. Well, don't you have to distribute? Don't you have to simplify that? So wouldn't this be 29 minus 4n plus 4 when you distribute? So wouldn't your rule be 33 minus 4n? Forgot to put the domain. And isn't the domain going to be greater than or equal to 1, less than or equal to 6? The recursive rule, which we still don't understand yet, you'll see when I do an example, is f of n minus 1 plus d, where n is 1 more than the one above it, 2. We still don't understand that. Just hang in there, you will. So this rule is going to be f of n is equal to f of n minus 1 minus 4, where n is greater than or equal to 2, less than or equal to 6. Now, this recursive stuff, I'm going to explain it in a problem. But for now, this is how we're writing the rules. All right, now, this is the first objective. We're going to graph these now. Anybody have a question about these? Okay, now, when we graph an arithmetic sequence using the explicit rule, we're going to use the calculator table. But unfortunately, with recursion, the recursive rule, we can't use a calculator. It's too hard. So anyhow, so this is the second objective. We're going to graph arithmetic sequences. And I'm going to give you a couple more definitions. A finite sequence. Now, I'm not saying finite arithmetic, just a finite sequence is a sequence with a final term. So, for example, if you had 3, 7, 11, 15, 19. This is how you write a sequence, by the way. You have to separate them with commas. This is important because an arithmetic series is going to be separated with plus signs. Now, an infinite sequence it has infinitely many terms. For example, 3 dot. Do not put 4 dots. Do not put 2 dots. It has to be comma, 3 dots. Those are called ellipses. Can I erase this? So here we go. It says write the terms of the, so they're telling you it's arithmetic. That means it has a common difference. And they're asking you to graph. All right, so they're going to give you a rule, f of n is equal to -1 plus 2, and that looks like explicit because there's no function in it. And they're going to say for this domain, n less than or equal to 4, greater than or equal to 0. All right. Okay, so get your calculator ready. Here's what you're going to put in the calculator. In the equation editor, y equals, you're going to put -1 plus 2x. And instead of graphing, because it's not going to give you the right graph, instead of graphing, you're going to look at the table. And you're going to tell me what, when n is 0, what do you get? 1, 2, 3, 4. Okay, so once again, put this in the equation editor and go to second graph and give me the values out of the table. So what's 0?
-1.
What's 1?
1.
3, 5, and 7. Okay, was everybody able to get that? Yes or no?
Yep.
Okay. So we're going to graph. Our x-axis is going to be n, and our y-axis is going to be f of n. This is going to be 0, 1, 2, 3, 4. On the y-axis, you're going to have 1, 2, 3, 4, 5, 6, 7, and you're going to graph the points. So 0 down 1, right 1 up 1, right 2 up 3, right 3 up 5, right 4 up 7, and should I connect them? Well, what does n represent?
Number?
Position be a fraction like 1 and 3.5?
No.
No. So the positions have to be 1, 2, 3, 4. And if you connect the dots, you're saying the positions can be fractions and radicals, and the positions cannot be any of that. So that is the graph for the arithmetic sequence. All right, now let's look at the recursion, okay? All right. First of all, the rule is f of n minus 1 minus 0.25 greater than or equal to 2. Now, if you're going to be a computer programmer, computer scientist, you're going to use recursion a lot. In fact, in my first computer course, we had to write a program involving recursion. I didn't even heard of the word. So at least you're being exposed to what recursion is. All right, so here we go. We know that the term in the first slot is 4. So when you go to the second slot and use the formula, this would be f of 2 minus 1 minus 0.25. Now, do you see what I did? I put the 2 in. And isn't 2 minus 1 f of 1? So you see how this is requiring the first term? And do you realize if they didn't give us the first term, we can't do the recursive rule? So what's the first term? What's f of 1? Who's in the first position?
Four.
So what's 4 minus 0.25?
3.75.
Okay, then we go to position 3. So now we have f of 3 minus 1 minus 2.5. Well, isn't this f of 2? So what is this requiring? What's f of 2 mean?
Isn't it 3.75?
Yeah, it's the second term. You guys there?
For me.
Yeah, same here.
Aren't we having fun? Such a joy, this technology. And the problem is this, I don't know if it's me. I don't know if the district is messing around with the network. So that's what's so hard. I don't know what's going on. So, okay, let me say this before it cuts me out again. Do you see how they gave us f of 1, f of 2 required f of 1, and this one's requiring f of 2. You see how every step is requiring the previous step? That's recursion. Okay, so let's go to 4. So this would be f of 4 minus 1 minus 0.25. So wouldn't that be f of 3? So aren't they asking for the third term? Well, let's finish this one. What was this?
3.50.
So back over here. What's f of 3? All right, I'm almost done. Let's see if I can finish here. You guys hear me?
Yeah, I can hear you.
So f of 3 would be 3.50, right? So that would be what?
0.25.
3.25. And if we went one more, this would be f of 5 minus 1 minus 0.25, which would be f of 4. So what is f of 4? That's the previous term, right? Right? Yes?
Yes.
All right. So I'm going to pull this down. Can you guys see the graph that low?
Yes.
This is kind of distorted, but I don't care. Actually, I can't do it that way. You guys. And write 5 up 3 and do not connect them. Okay, now that is the lesson for today, this part 1. What I want you to do is I want you to go into your teams and you're going to work on this. And we're going to come back, hopefully. Class ends at 12:10. We're going to come back at 12:05. And we're going to work problem number 15 together. Because in third period, I saw a bunch of people doing weird stuff. They looked at the answer and solved it all wrong. Everything was wrong, but they came up with the right answer, which is really scary to me. So you're going to work on this in your teams. Come back at 12:05, hopefully. And then we'll go over problem number 15. Okay, any questions? All right, I'll see you back here hopefully at 12:05. Okay, I'll see you in your teams.
Miss Birch, could I take a picture real quick of the whiteboard behind you?
Yeah, but in the future, you're gonna have to write quicker. You're gonna have to write quicker. Leslie, are you there? Did you get it? All right, and we're back. Okay, can you guys hear me? When you square both sides, you have to check. Because in problem number 10, there's no solutions. So you get a quadratic and you get 2 possible solutions, but they both fail. And if you don't check them, you're going to miss the problem. Now, when you cube both sides, you don't have to check. But when you square both sides, you must. Let's take a look at problem number 15, because I watched period 3 solve this, and it stressed me out. So what they did, they wrote a bunch of garbage and wrote the answer, and that's never going to fly with me in class. So in number number 15.
Miss, can you pin yourself if possible?
Yeah. It says, a biologist is studying 2 species of animals. The population of 1 has that formula, and the population of 2 has the other formula, and T is measured in years, time. After how many years will the populations of the 2 species be equal? What do you think you're going to do? Aren't you going to set them equal? And solve for T? So the first thing I'm going to do is divide by 100 and divide by 100. Now I'm going to get rid of the power by multiplying both sides by 2. Now, when you multiply by 2, isn't this going to become 5 squared? Pay attention. It becomes 5 squared, doesn't it? Yes, no? Somebody say something.
What?
And this would be T cubed. And this would be T to the 4th. Right? So what you have here is you have 25T. Well, don't you have a quartic? So isn't the only way you know how to solve this is you doing a P over Q list or synthetic substitution, but don't you want to factor? So don't you want to do a GCF? Yes or no?
Yes.
So take out a T cubed. So that would be T. T cubed times what is that? So what are your 2 possible solutions? What makes this 0?
Zero?
What makes that 0?
25.
Well, in this real life problem, 0 doesn't make sense. 0 years. And I didn't see anything like this in period 3. They did nothing like this. And I'm like, what's going on? Like, aren't you supposed to isolate the variable? Aren't you supposed to solve it by setting it equal to 0 and using the 0 product property? Can't forget everything we learned, right? Questions about this? All right, listen, I hope you guys have a great weekend. Don't forget about the exam on Tuesday morning, right? Remember that you can study together in the teams anytime you want. All you do is you can go at 9 o'clock at night and get into one of the Math Wizard teams together. So, all right, I hope you guys have a great weekend. All right, I'll see you soon.
All right, have a good weekend, Ms. Birch.
Have a great
Thank
weekend,
you.
Miss Birch.
Bye, guys. Have a good weekend.
Bye, Ms. Birch.
Bye, guys. Sorry about all the technical issues.
It's okay. Bye, Miss Birch.
Bye, Leslie. Have a good day, guys.